Hello, welcome to Recitation 2, where we'll be talking about the tools you'll be using for this class. Namely, the most important tools would be Numpy and PiTorch. There's a big list over here. I basically just typed import and anything I could think of at the moment. So this begs the question, why do we even use a framework? I mean, after all, Python is Turing complete. You can do whatever you want just by writing a few lines of code. But then, like, for instance, matrix multiply, it didn't take too long. I could just write it like this. Just given two matrices, which are lists of lists. I can compute what the matrix multiplication result is, store a new list, return that. Why do we even need something like Numpy or PiTorch to do this for us? So it turns out that Python is very bad at doing computations in general. So this is my version of the matrix multiply. I don't know if you can see. It says 177 milliseconds. I think I used a size 1000 array or something. And the same version, if I written it in Numpy, takes more than 1,000 times less time. It was 2,400 times faster. This is very strange. Python is not very efficient for this kind of operation. So not only are frameworks important for the usual reason that everyone tells you to use frameworks, namely they contain all the library functions so that you don't have to write anything on your own except by you can just use the library functions to write your code in a high-level style. Not only that, in Python it's pretty much required to do anything without waiting eternity for it to finish. What happens is that it just vectorizes your code. It pushes all like the inefficient Python loops into kind of the library loops, which are not written in Python, which is why it's all the faster. So let's start with Numpy. This is basically like the core of all numeric computation in Python. A lot of the other libraries are built on top of Numpy. Basically, what it does is it gives you access to kind of arrays as you see them in other languages. They can let you perform computations that apply to the entire array. So for example, you can just say, create an array of zeros, and it'll automatically, I don't know, allocate memory, fill every element with 0, and so on. You can say, you can make another array that contains every other element. You just type one line, and suddenly it would copy every other element from the first array to the second. You can say, just add 1, and it would add 1 to every element, and so on. There's all these operations where you just have to specify one operation, and it applies to every element inside the array. So you don't have to like write a loop that goes through each element, which would still do the same thing, but now your loop is in Python, and it'll be slow. And so much of this demo about Numpy will be on it'll be on a Jupyter notebook. So I mentioned this before the recitation started. So for now, people who are just coming in, I would suggest just using the GitHub link. It'll also show you the results of running each operation in the Jupyter notebook, but it's less interactive. You don't get to run each operation, alter the values, and see what happens. But I think we have a pretty complete selection of things we want to talk about. So everyone has laptops, right? If not, you might want to bring them out.
Any last minute questions on getting on to Frank's notebook? Questions about how the font works? Everyone can get in. Okay, raise your hand if you actually have Jupyter Notebook running. Would be a good way to do it. Okay, so peek over those people's shoulders if you can't get it running, and then ask us for help later.
Yeah, we'll help you set up AWS after the recitation ends, because office hours happens immediately after. How long should I wait? How long should I? I'll just start.
I don't know where the slides are.
Oh, you don't have the slides? You just go to Piazza, and it's in the. It's in the links where it says like your recitations, and then there's a link next to it.
We were taking them off Dropbox, so we were taking them off Dropbox.
Okay, yeah. No, this is the current. The current is the one that's linked on Piazza.
Yeah, give me the thumbs up once the stream is ready too.
Jupyter is running, and it's running at all IP addresses.
That's
on your
interesting.
system. So this is like we did in the last recitation. You should be able to type in the IP address of your server, whatever that is.
Okay, then what is this? He says there's no torch.
No module name torch probably means you didn't activate the environment.
I have already activated it.
In the upper right, it will say which one you're running here. So it just says Python 3, right?
Yeah.
Yeah. If you go back, yeah, this is probably not activated.
Jerry.
Torch.
Good.
Yeah. Right now,
You don't have to clone it. You can just visit it
if you get into
directly.
Python right here, you should be in the right environment. If you don't, is this the
No,
the
you can just use
Amazon
Notebook.
AMI? The deep learning AMI? Or which one is it? Yeah, questions like that. Your IP address of your AWS instance will be in your web dashboard on AWS. So I think we'll just have to go on with the tutorials. We do have a lot of content to cover. Is there any quick questions about what get on or? Okay, and if you want to just keep trying to get on while you 90% are looking at the slides, that's okay too.
All right. So just moving on. Like if you haven't gotten the page set up, it's okay. You can just look at the slides. We'll go through it.
Has anyone used Jupyter before, by the way? Everyone kind of knows what it's for. So Jupyter is really good for combining your text and your code and being able to run them interactively. You change them. It's kind of the choice for like making your apps, things like that. So I guess.
Okay. By the way, how many of you have used Numpy before? It's a fair number. There's some things in this notebook that even I didn't remember before, like creating it or reading Ben's creation of it. So let's start with the basics. To create an array so that we can actually do anything on it, there are several ways. One of which is to just pass in a regular Python list. So we can say mp.array of this list of 4, 5, 6, 7, and then we get the Numpy version of the list, which still contains 4, 5, 6, 7, unsurprisingly. We can do this with a higher dimensional array. So like this is a list containing a list, so it would have dimensions 2 by 3 if it were a matrix. And so if we turn it into a Numpy array, again, it shows us that this is the structure of the array. Oh, yeah, I should probably. And there's also several ways to do it that don't rely on clunky Python arrays. One is, first, this call is not important for now. It just means set up the random number generator. What we do is we can say, let's create a random array that contains 9 elements. This funny tuple thing with like the 9 and the comma is basically saying what the size of the array will be. In this case, we're saying it's a one-dimensional array, and it has 9 elements. And so with doing mp random of 9, we get an array that contains 9 random elements. It should be a uniform random 0 to 1, like exactly how we typically create random number generator without any other options. We can also do random integers. For instance, this one would create random integers between 0 and 3, not including 3. And so it would create several 0s and 1s and 2s and so on. Again, it's size 10. It's still one-dimensional. There are special other types of arrays that we can create, such as the identity, or it would be the identity matrix. What we do is just say we want a 4 by 4 matrix and its identity, and it gives us this thing. We can also just create an array full of zeros. You'll see this very often because it's kind of the default when we don't know what we're adding in yet. So we could create an array of zeros and start writing into it or something. We could also do 1s if we wanted to. And there's also a range, which basically means include all the elements up to 6. It's like how range works in Python, except it creates your array instead. So any questions for this part? OK. So every ND array, which is like what we call the Numpy arrays, they're called ND arrays, they have several properties, one of which is the shape. So the shape is the thing that we've put into the tuple. It's like before we had 9 comma nothing else, and then 10 comma nothing else. We could also have more dimensions, 2 comma 4. Unlike something like MATLAB, we can even have higher dimensions. We can have like 3-dimensional, 4-dimensional. Actually, I think MATLAB supports that too. But there's like it's nothing special about 1 or 2-dimensional arrays in Numpy. And we can also ask for the type of the elements inside. For instance, this is an array that contains integers. It's 32-bit integers to be exact. We can also typically we use either floats or integers, not doubles, because like for machine learning purposes, 32-bit floats are usually enough. And so now we can get into fancy ways to index arrays. So the normal way to index is just the typical like index of number 3. It gives you a single element. But then often we want kind of different indexing strategies that give us more than one element. Because if we can only index one element, then pretty soon we'll be doing really slow arrays that like modify one element at a time. So what we can do is, number 1, we can use slices. So this notation that says 1 colon 5, it means take the start from element 1 and go up to, I think it's up to 5, not including 5. It's similar to the syntax you would have in Python lists. We can also not specify the start and the end, which would do exactly as you'd expect. It'll start from the beginning, or it would go all the way to the end. There's also this syntax, which is saying we can have a start, we can have an end, and we can also have like in a step size. So this one gives us the X array, but then with all the elements in reverse order. We can mix any of these. We can have a slice that has reverse order. If we want, we can also go every other one. And with this last one, we can access every element in the array. This does nothing by itself, but it's pretty useful in other ways. Like in a sense, it flattens the array, and like it lets you access all the elements in a uniform way without having to deal with indexing everything. So a little note, this syntax, like this kind of syntax also exists in Python, but then the order is different. Like I remember the step size is in the middle for Python. So just a little thing to be careful of. And also, all of these operations are constant time. They don't like create copies of the array. So if you modify one of these slices, you modify the original array as well. And so this time, this is a different kind of fancy indexing, which is we can index using another array. For instance, we have this I variable, which is the array of indices. They're random numbers between 0 and 10. We have 5 of them. And this is what we end up getting. We can access X with these 5 indices. Let's see, what was the latest value of X? X should be this value. It's the square numbers. So if we access 4 of X, we get 16. Access element 1 of X, we get 1. Access element 7 of X, we get 49. So you see how this like array-based indexing works. It's very useful to like instantly access all the things that you want in the array. And you can basically do a combination of all of these, one for each dimension. So if Y is a two-dimensional array, we can say we have Y is equal to the reverse of X for like the first dimension and the array 3, 4, 2 in the second dimension. And let's see, what would be the result of Y? We're accessing X over here, so we're accessing every element of the first dimension, but only elements 3, 4, and 2 of the second dimension. And that's what Y would end up becoming. For the original X was a 2 by 5 array. The final Y, for dimension 1, it always includes both values, but for dimension 2, it only includes the ones that we specified here. So let's see, number 3 would be 0, 1, 2, 3. X is both. Which one's printed? Which?
It's just reversed.
Oh, it's reversed. So
6, 5, 2, 9. 2,
oh yeah, it's reversed. We have 6, 5, 4 shown up over there. 2977 showing up here. We have number 4, which would give you 37 over here and 49 over there. And using this syntax will also help us set values. So what we often do is we use a fancy indexing strategy to select the part of the array that we want to modify, and then we set that part to some value. So this one, this just sets a single value of the array. So we originally have a 4x2 emp0 array. We set the 0, 1 element to 1, and then we set the 3 everything else element to 2, and this is the result we get. And there's this, we can also mess with the sizes a little bit. So this is a 0 array of size 3x5. We can select the first row of the X array and set its value to a 5-dimensional array, a length 5 array, and it'll set up the value for us. So we'll get to broadcasting very soon. In this case, the size of the shape of x1 colon is the same as shape of NPA range 5. So it works out. Sometimes you can get different sizes. We'll show you later. Any questions for this part? OK. And there's this. We can use conditioning to also select elements instead of just saying we want exactly these positions, which are specified in advance. So for instance, we can create an array of random numbers, x again, and we select all the ones that are greater than half. So what this syntax, x greater than 0.5, does, it doesn't give you just a true or a false, as you might expect from like a greater than sign. It instead gives us an array of trues and falses, which compares each element to 0.5. So like, if you have code that says, if x greater than 0.5, then do something, then something's gone wrong, because an array is always not false.
It will actually give you an error in Python saying that like, an array can't be evaluated as a Boolean or something like that.
Yeah. So that's something to keep note of. If you do a Boolean operation on an array, it gives you another array of Boolean values. And then we can index the original array x using this Boolean array. What it does is, for every place where it's true, the value is included. For every place where it's false, it's not included. So it includes this part, and it doesn't include the next one, doesn't include the next one. It does include this one, so it goes in. And the end result of this operation is that we created a smaller array that contains all the elements from x that were greater than 0.5. And there's several ways to do this. One is the Boolean array method, which is what we did here. The other one is we can basically extract the indices of the places where it's greater than 0.5. So what we do is, again, we have this. This is an array of Boolean values. There's this function called non-zero, which it gives you the indices of all the places in the Boolean array that are true. So one little hint about Boolean arrays is that you can just think of true as 1 and false as 0. Like what it prints out is just a kind of prettier syntax of that. So you can even do funny things like you can take the sum of this Boolean array and it'll just add up all the trues. So anyways, so it takes you all the non-zero elements, which means since false is 0, it gives you all the locations of all the true elements inside this Boolean array. And what non-zero does, it returns 2 things. One is the indices, and one are the actual values. So we know that all the actual values will be true, so we can ignore that, and we take the first array in the result.
Non-zero returns a list of indices, so it's 1 for each dimension, actually. So there's only one element in this list because it's just a 1D array. But if you have like a 2D array and you run non-zero, it'll return one list, which is all the x, or all the I coordinates, and another list, which is all the j's.
Oh.
So however many dimensions it has, it'll have that many lists it returns. We just only care about one. Example.
Sorry, yeah. It only returns indices, but it returns a list for each dimension. So in this case.
Is that why you're asking for the 0th element of what non-zero returns?
It's not the 0th. Yeah, the 0th element is the list of indices in the first dimension. We just don't have other dimensions.
So the result of this will be an array that contains an array that contains this thing. It's an array that contains this thing, so it's like nested. So if we take the 0 element, we just get the one and only element in the outermost array. And so there's another function that's called take, which will basically access the elements in X according to the indices that you've told it. It's, I think it's a special syntax of just doing it the normal way.
Yeah, you could do it in brackets. This is just.
So yeah, like in this case, it's just we're showing the more explicit version of how it can be done. Like this one can also be done with the fancy indexing that we've shown earlier. And any questions?
Can you change it to the array to show the result?
This is just a GitHub rendering. We didn't want to worry about the display. So we're starting off a new computer.
Okay.
But if you have Jupyter working, or if you want to come by office hours, we could definitely do that.
Okay, yeah. And so over here we have some other, there's some functions that do specific indexing patterns that might show up in certain applications. Like in this case, there's a function that accesses all the diagonal elements of X, just np.diag. And there's another one that gives you all the indices of the lower triangular section of the array. So like, again, this thing gives you a 2-dimensional array, which contains like a list for each dimension.
It's a good example of what you were asking about.
Yeah, so like, I guess I can go through this in a little more detail. So X is our 5 by 5 random matrix, and TI trial is the lower triangular indices. For instance, we have, this is the result. It's a list of arrays. So the 1 0 element is going to be in the lower triangular. It is. The 2 0 element is. It is indeed. And where's the, I mean the 2 1 element is over here. It should be, oh, this is the lower triangular indices that are just one below the diagonal.
Not on the diagonal, it's below the
Yeah, so it's like right next to the diagonal, but below. We can print out the values that are in this like near diagonal position, the lower triangular one below diagonal location. And then we can set the entire value to 0 to 3. Let's see, we get the 3s showing up at this position. It includes every element that's right below the diagonal.
So what would be a situation where you would need to do something like that?
A lot of time covariance matrices. Like a good example is when you're doing reinforcement learning. You're trying to learn the you fit a quadratic, and you do that by like trying to make something that's positive definite. And the way you make something that's positive definite is you fill out just the lower triangle. So to make a positive definite matrix, you only need to parameterize those. So you have like 7 or 8 elements in your parameters. You put them into like a full thing so that it's empty on one side, and then you multiply it by the transpose, and then you get a positive definite matrix, and you go from there. Oh, sorry. Yeah, sometimes when you're trying to like construct a positive definite matrix, or you're trying to do other things, having just the lower or upper triangle is really useful. And a good example is covariance matrices too, that like they're all symmetric. You don't really care about the other side. So if you wanted to get just the data that's relevant, and you know in covariance matrix that the diagonal is going to be 1, so who cares about that? So if you're doing something like parameterizing it or looking at the data for it, you tend to use the lower triangle. Because the diagonal you don't care about, and everything else is symmetric. You know that's 1, you know it's symmetric, so it's the relevant part, basically. Do what?
Blob diagonal.
Not really. I mean, you could do. Actually, yeah, there's a pretty easy way, which is you can do the diagonal elements, and then you just shift the whole thing. Because these are all arrays, right? So if you generate the diagonal of this matrix here, and then you add 3 to the I indices, and you add 2 to those indices, and you're just moving it around. And this is what we were talking about earlier, that you can index arrays with arrays, and those arrays you're indexing with, you can multiply, and you can add, and you can whatever you want. So it's kind of pointer logic-y. If you guys,
Yes.
I don't know if you guys used to do C++, but some things you do with Numpy and PiTorch actually look a lot like the pointer logic you used to have to do.
Yeah, so like you can build, say, an entire block at once, or you can like build all the blocks simultaneously, a few elements at a time. There's several ways to do it. And so this is another syntax we can use to create one-hot variables. I found that, so I was a little bit confused what it was actually doing until I looked into it further. What it's doing is there's like a one-hot variable in each of these locations. And so like there's guaranteed to be a 1 along one of the dimensions, but then like the location is randomized in this case. So what we do is there's this function called mgrid, which gives us this thing. It gives us the zeros over here in this dimension, and then zeros 1, 2, 3 in that dimension. So we can make this in with a range if we want. It's just a library function helping us do it more quickly. And then what we do is we create another array of random locations. So we have x is where we're writing into. The I is like the values that we're going to put. It's a 5x4 array of values, either 0, 1, or 2. So like we have another array of this shape that has like 0, 1, or 2, 0, 1, 2, 0, 1, or 2. And what we do is just we use the fancy indexing to give each element of these we create a one-hot variable with 3 possible values in all of these like 5x4 positions. Basically, like this is what the mgrid is most useful for.
Any questions about mgrid? That's a tricky one. Mgrid is how many. What mgrid does is it gives you the indices for.
Oh yeah.
Okay. Mgrid gives you the indices for a given matrix. So like, imagine you have a matrix that's got 4 dimensions, or let's just start with the 2-dimension one. I guess we can scroll up. But like the. Sorry, I feel umbilical cord here. Yeah. So like, if you imagine an array of this shape, the x, like the row coordinates of each thing go here, and these are the column coordinates, and that continues for however many matrices you have. So, or for however many dimensions you have. So mgrid, like each element of the mgrid is the indices along each of the axes. So then we're just adding an extra axis. So it's the same first axis, same second axis, and the third axis is our variable. So I guess it's a little tricky to understand when you first look at it, but this type of array indexing and mgrid really, like, you completely avoid loops here, basically. But yeah, I mean, it's it does extend to as many dimensions as you want. If you write mgrid :5, :4, :7, then you'll end up with 3 different arrays, and each of those arrays will be 5x4x7.
Mm-hmm. So it doesn't really help that the default display is not like the most intuitive for this, but you can see that there's like 5 of these, and each one has 4 rows, and these 3 values are showing you the one hot value inside each like position in the 5x4 grid. And so there's this another operation that's very important. It's called reshaping. It basically changes the shape of an array by like moving all the elements appropriately. So basically, the assumed order of all the elements would be row major. So this is the assumed elements of order of all the elements if it were a one-dimensional array. So what happens when you reshape is you get this like the new shaped array, and it places the elements inside with the same order from the original and the destination. And so there's like several reasons why you might want to do this. Like this is different from, let's see, if do you have later? I'll get to that if it shows up, but like sometimes you want to like move a size, like a dimension 1, a size 1 dimension around, which will, and like to do this you can do reshape, and it'll usually do what you want. There's also a transpose operation, which basically you can transpose along several different dimensions if you want. So the .t by default would work with a 2-dimensional array. If you do it with a higher dimensional array, you can specify which 2 dimensions you want to transpose with the more verbose syntax np.transpose. And you can also do things that add size 1 dimensions or take them away. So if you think about it, a size 1 dimension doesn't really affect the the kind of like data inside the array, although it changes its shape and therefore your code would crash if it has the wrong number of dimensions, even if one of them is just size 1.
I would point out in the transpose, it's a little different than there are some frameworks where transpose, you give which two axes to swap. In Numpy, you give it what is the order of the axes that you want them to be after the transpose. So you can transpose multiple dimensions. If you have like 10 dimensions, you call numpy.transpose and then 7, 2, 5, 9, 8, whatever. That means it'll move the 7th to the 1st and the 8th, whatever it is. So it's multiple dimensions, can be transposed as many places as you want. But the indices you're giving there are which axis should be moved to that location.
All right, and then so what we do is we can do expand dimension to add a size 1 dimension in the kind of position number 1. So that gives us originally we had the 2, 3, and 1. We added a size 1 dimension into position 1, so it's now 2, 1, 3, 1 is the shape of the array. We can also squeeze, so it removes the. So squeeze would remove the dimension. In this case, it was the dimension of 0, 1, 2. It removes dimension 2 if we 0 index, so that now we have a 2 by 3 array instead of a 2 by 3 by 1 array. And so there's a concatenation operation, which will basically do as you expect. It will put the arrays together if the sizes are wrong. You have a question?
Yes. So I have had sometimes trouble when I have, well, I think it's a one-dimensional vector. It's, for example, shape 5, comma, empty.
Mm-hmm.
Sometimes it's 5, comma, 1. What is the exact difference between those?
So the question was like, what's the difference between a 5, comma, empty sized matrix array and a 5, comma, 1 sized array? So basically, the first one is like, in its heart, a one-dimensional array. So like, if you ask number of dimensions, it will give you 1. If you do any operation with other one-dimensional arrays, it will work as you expect. The 5, comma, 1 array is by its heart a two-dimensional array. It's considered like a row vector, sort of. Is it? No, it's a column vector, 5 by 1. And so if you try to add it with a one-dimensional array, it'll try to do broadcasting or something. The rules become very different, even though the data is the same. And so there's the stack operation, which basically does concatenate while assuming that all of your elements have like size 1 in the extra dimension you want to create. So in this case, we have a random array of size 2, a random array of size 2, and they want to stack them without like first creating an extra dimension for each and doing concatenate. So what it'll do is just, because it turns into a 1 by 2 and a 1 by 2, and it stacks these two together. And so these are the linear algebra operations. There's like plus, minus, times, divide. We can do mean, square, square root. Dot is the matrix multiply operation. And so this would give you the mean. You can do the mean as normally. You can square each element, take the square root, so on. And so there's the broadcasting rules that I've been talking about all the time. And so for these, there's several rules we want to do this. First of all, this is a two-dimensional array. We can add constants to most of these arrays. It will reshape the constant to match the size of the array you're adding to. So in this case, it'll add 0.3 to each element. This one, we're creating a 3 by 4 reshaped array. And we're adding we can have, in this case, what broadcasting does, it adds the appropriate sizes to this, it adds like extra dimensions to one of the operands so that they match. As long as they have the same sizes in the ending dimensions, it's fine. So this is like a 3 by 4 array. We can add repeated 3 times in order to get added correctly. And we have a size 3 by 1 by 2. The 1 is okay because like when you have a size 1, it can also get repeated 3 times to match with that. This is like the explicit way to get around the requirement of only matching in the end. So like if we wanted to repeat 4 times and have like a size 3 array to add to this array, this like 3x4 one, we can make a size 3x1 array to add into it, and it'll do the broadcasting correct. Any questions about this? And so if we break the rules with broadcasting of other operations that require matched dimensions, we get an error. Lastly, we have this saving operation. So we can save array x into this like file temp.numpy, and then we can load it, and it would give us the exact same values. It will just create a file that contains everything we need. And we can also we can save multiple values at the same time. And when we load, we end up with some kind of dictionary. And so we can access the appropriate value of the dictionary and get what we need. Any questions? OK, so I think we have to move on to the next part.
And I guess one last thing about saving and loading is there's also a save txt, which will save it as a text file instead of a numpy file. Sometimes handy if you want to be able to just browse it and look at it.
All right, so you're the PiTorch part.
Oh, yeah, I mean, because you run your model and later you want to run it again with the same data. Or a lot of the data we're going to be giving you in the class in Numpy, it's become like a very, very standard portable format. So like, in general, when you go out and you download some like CFAR 10 examples or something, there's a good chance it's going to be in Numpy files. Everyone likes them because you write 0 code to open them. It's just like numpy.load, path, you've got all of your data in an array, and then, you know, do the machine learning. Does it, like, check or whatever? Does it work? OK, anyways, if you guys get out of that notebook into the parent folder and then switch over to the PiTorch named notebook, I'll give you guys a second to do that. But we're more than halfway through, so I do want to keep it going. So let's pull up the PiTorch version in the notebook. So PiTorch is the framework we're going to be using. One thing that's missing in Numpy, or two things that are missing in Numpy, are it does not use the GPU, and everyone knows GPUs are good for machine learning. And it doesn't support automatic differentiation, and nobody likes to do their own calculus. And PiTorch is what steps in for those two things. But in the back, the reason we talk about Numpy first is it's inspired by Numpy. You use Numpy to interact with it. Everything kind of goes through Numpy before it gets to PiTorch. So with that, here's a PiTorch tutorial. First, we're going to talk about just how to use PiTorch and do calculations. And then we're going to do another example where we actually show you how to put it together and train a model. So as we said, GPU accelerated, automatic differentiation. And it also has utilities and some framework code for neural networks. Help you out. So everything in PiTorch is a tensor, kind of similar to your Numpy ND array. Very similar kind of syntax, indexing. They have floats, they have integers, etc. The main way you create it is, keep going through. Torch.float tensor is kind of your basic way to just create a float tensor. And then tensors have an underscore function. If you see a function with an underscore in PiTorch, it means that it's actually modifying the data. It doesn't return a copy of, well, it also returns a copy, but something like 0 underscore modifies what x is. So it creates a tensor. When you create a tensor, it's always uninitialized, just as random junk in it. And then after you run 0, it sets it to 0, and then prints it out. It's just a regular tensor. So as I said, a lot of times you come from Numpy. So if you create a Numpy array, you can take that Numpy array and put it into Torch. Here are kind of two ways to do it. One way is from Numpy. From Numpy means it uses the data type of the Numpy array. So if you say from Numpy and you give it an int array, it'll give you an int array, et cetera, et cetera. Or you can explicitly say make a float tensor from it. That's pretty straightforward. Here is the, by the way, seeding for Torch. If you want to make things repeatable, manual seeds are nice. So instead of just creating it from Numpy, similar to in our Numpy tutorial, you can just generate random data off of the GPU. For example, rand_n, random normal. If you look in the docs, there are a bunch of different random functions for integers, uniform distributions, whatever. But it has a random library. There are also certain special tensors you tend to use. These are very similar to the ones we talked about in Numpy. So I'm glad we can skip through a lot of this because it's very similar, but you can create I matrices, you can create a range, all of the things that you expect to do, they're counterparts, but the main difference is these can be run on the GPU and they come out with float tensors instead of Numpy data. Similar to Numpy 2, they all have a dot size and a dot type. Note that these are functions versus they're methods versus in Numpy they were properties. Yeah. But yeah, so there's sizes and there's that. So one of the important things that we talked about is being able to use a GPU. So in Torch, what you have to do is you have to put things over to the GPU when you want to have them on the GPU. And you got to bring them back from the GPU when you want to actually use them on the CPU. So you do have to be conscious of where things are. So if you have x, this is just a Torch tensor. When you call x.CUDA, it returns a new tensor, which is a tensor that's actually living on the GPU. To get it back to the CPU, you call .CPU. So x is on the CPU, y is on the GPU, z is back on the CPU. When you have something on the CPU, you can call .Numpy to get it back into Numpy. So we showed you how to get it from Numpy into a tensor. Then you can get the tensor to the GPU. You can get a tensor from the GPU back to the CPU, and then back into Numpy. So that's a lot of steps to go into the GPU and back, but those are all the commands that you would need to know. So you see here, if you ever print it out and you want to see what it is, if it's torch.something tensor, that means it's on the CPU. If it says torch.CUDA something, and then it actually says which GPU it's on. So if you're looking at your tensors, you can see what it is. What's very important is that you, so for example, this happens when you try to call .numpy on a GPU array. It'll say, I can't do that on a GPU array. So you always have to go .cpu.numpy. Right?
Slow the tempo down a little bit.
Oh, sorry. I was trying to keep up with the scrolling, actually. If you scroll a little slower, I'll go at the speed of the... I was trying to go before it went by. OK. Also, what's important is you can't mix between the GPU and the CPU. If you've got a tensor on the GPU and a tensor on the CPU, you try to add them together, you're going to have an error. So in general in this class, everything goes on the GPU because you want things to be as fast as possible. And another question?
Question from the stream. When would you want to do operations on the GPU versus on the CPU, like, as opposed to just letting the library decide for itself?
Well, what's interesting is the library doesn't really decide by itself. It is PiTorch, and PiTorch does require a lot of kind of hacking and manual boilerplate type stuff. So pretty much everything you write in PiTorch is going to have code at some point which says, if CUDA is available, then move everything over to CUDA. So you will actually, unfortunately, end up with some if statements or command line flags to check to see if you want to do CUDA. In general, if you're writing code just for yourself and you know it's always going to be on CUDA, then you don't really need the if statements. But if you want something to be portable and well-designed and all of that, then you will want to have something just to check to see if CUDA is available and move it to CUDA if it is, things like that. But in general, if you want things to go quickly, you will be using, you should prefer GPU if it's available. But for example, the non-GPU, yep, sorry?
Is there a command where you can see what is already on the GPU?
The main thing is torch. Is CUDA available? Is underscore CUDA underscore available? We will get to it in this slide. I'm not sure. I don't remember exactly the title of the method, but it'll tell you if CUDA is available on your machine. And where this will come up is if you guys are doing development on something that's CPU only because it's cheaper, and you want to be able to just run it and see what's happening, but you don't care if it's slow because you're debugging your code. You just want to run one iteration to see if it's failing and see if it compiles. Then you can do something like this, and then when you move it over to your actual expensive GPU machine, have something in your code which will switch over to GPU when it's available. So that is a little bit of boilerplate that you're just going to have to get used to with PiTorch, but that kind of comes to the territory.
Yeah, kind of another point, like, the reason why the library kind of doesn't automatically move things to the GPU when needed to, like, make things match is that, like, PiTorch is very, like, transparent about how it would, like, all the performance costs of all the operations. So, like, moving things to GPU does have a very significant cost. If it hit it for you, then you have like weird performance issues there. It's really hard to debug.
Yeah, that's actually a very important point, is it's not free to move things over the GPU. There are some times, if you're working on something small, that it's actually going to be faster to keep it on the CPU if the amount of operations that you're doing is not so high. And also, it supports multiple GPUs on PiTorch, so occasionally that's useful because you want to manually put this stuff onto that GPU and this stuff onto that GPU and actually do some GPU management, but you guys are not going to be worrying about that in this class. I think one GPU is enough for you. But here's just an example of if you have something that's not on CUDA and something that is on CUDA, and you call matrix multiply, this is the error message you're going to see. Recognize that error message. If you ever see it, then you'll know what to look for. It is the kind of the standard style of error message PiTorch gives you, which is invalid combination of arguments. It says what it got and then what it expected. And the main thing to look for is it says, it got float tensor CUDA.float tensor, but it expected float tensor. So that's saying it got a CUDA, but it expected a regular.
Yeah, so this often happens even like when you're working in the high level. Like you put something into your RNN or like your convolutional network, and then some very far down the pipeline it says, oh, I had CUDA tensor and float tensor. And it's like a function you didn't even write. But basically it just means you got something wrong, like combining CPU values with GPU values at some point.
You will get this error at some point in this class. Learn to recognize it, and then you know what to do.
The exact contents of this message is less important than the fact that you see CUDA somewhere and not CUDA somewhere else.
Right. OK. So as we were saying earlier, if you want to be able to work on GPU or not GPU, OK, so it was CUDA.isAvailable. So that just returns a Boolean, tells you if you have CUDA available on your system. That means you have a GPU, you have the CUDA toolkit, you have NVIDIA drivers, et cetera, et cetera. So you kind of if statement like this, and what this just does is you create the CPU version. If you have CUDA, then you convert it over to CUDA, and you typically save it back in the same variable so that the rest of your code just works on X and doesn't worry about where X is. And then if you want to go back to the CPU, you can have this is the part, like, that's before you do your code. This is doing your code. You don't worry about if it's CUDA. And after you're doing your code, you can check to see if the particular thing is currently on the GPU. If it is on the GPU, then move it back to the CPU. So that's your overall move it if you need to, do something, then move it back if you need to. Something like these two loops you will have. Frequently, you'll put those into helpers or organize it yourself, but
more hackily, like it happens that if it's already on the CPU, you can still call .cpu.
Yeah, so that's good to know, right. You could do this even if it was already on the CPU, so
I guess
not just redundant it.
Yeah.
Yeah. So one thing that does help is the new function. This way you don't necessarily have to track what's on CUDA and what's not. So if you have a tensor, which is x1, and you call it .new, that creates a new tensor, which is wherever that tensor was. So the x1.new, the data of x1 doesn't matter. The only thing that matters is where it is and the type it is. So if x1 was CPU, it'll create a new CPU. If it was GPU, it'll create a new GPU. And that's convenient instead of having a bunch of if statements everywhere in your code.
Is new also copy value?
No. New, it's weird syntax, because when you say something.new, you expect it to have something to do with it. The only thing the new has to do with is like the device that it's on. So it's just kind of to avoid the if statements as a byproduct. So other than your initial data, pretty much everything you should be trying to use new. And you should be avoiding using the torch.float tensor constructor, because it's just extra overhead for you.
I've been guilty of like doing all the if statements to check if these are a GPU or not. It's very painful.
Yeah, it's something you'll develop your own style eventually and your own favorite ways of handling it, but it's ugly, but it's manageable.
In this case, if the x2 was not x1.new, but just another torch.ran, and you try to do some operation on x1 and x2, it would just say, no, they're on the same.
Yeah, I would say one of them is a CPU. Depending on which one was the first argument, it would say, I expected a CPU and I got a GPU, or it would say, I expected a GPU and I got a CPU. Just whichever order you do it, you might get the message reversed.
This is also very useful if you have more than one GPU, right?
Yeah, exactly. And also if you have more than one GPU, new is on that same GPU, so you don't have to keep track of which thing is on what GPU, but that's probably not something you're going to be worrying about.
So you do have two GPU
I'm sorry?
If you have two GPU, one is run on the first GPU, another is on the second, could they do the multiply?
No. You would have to move them from one GPU to another GPU.
Yeah, again, it's
So
very
it's-
transparent about when
Yeah,
operations
but-
is time.
I'm sorry?
How will this tensor initialize?
How's the tensor initial? The tensor, this dot new is not initialized. So what you'll do, like if you want zeros, you'll say dot new and then dot 0 underscore parens.
This is just what happened to be
Right.
in the memory at the moment.
Right. So actually, that's a good example. It's like this is just random junk that it had when it created them.
Yeah, it's not
It does
even
not
like a-
initialize anything for you. But the standard way to initialize is dot 0 underscore. Just make it zeros, or dot ones, or whatever the other, depending on what you want to initialize it with.
Just maybe mention that the underscore functions.
Yeah, we
all
did.
in
But
place.
yeah, all as we said before, everything that has an underscore means it actually modifies that particular tensor in place. It will also return a value, so you might think that it's just returning a value, but it's both returning the variable and modifying it internally. As opposed to if you see something that is like .CUDA, no underscore, your original value, your original variable is still fine. There's a new one that is CUDA'd. All right. Any questions so far? Any questions from the stream? We're kind of rolling through this pretty quickly. Yeah, so everything going on. So we saw that Numpy is much faster than Python, and by the same amount, pretty much, the GPU is way faster than Numpy. But Numpy is fast, so Numpy is a significant upgrade from Python, but GPU code is a significant upgrade from Numpy. But the one downside is, as it says, they are normally much, much faster than GPU calculations, but sometimes if you're dealing with small arrays, the cost of booting up your GPU and running the code on it overpowers just, you're multiplying two numbers. So like there are some times where it's better to do it on CPU, but in general for neural networks, big chunks of data, GPU is going to be faster.
So running through a 24 by 24 array of 3,000 images.
Yeah, once you get 3,000 images, yeah, that's definitely GPU. But if you if you're just you've got 30 losses and you want to get the average, you're probably better off just doing Numpy mean as opposed to trying to get it into a tensor and putting it on the GPU and getting it back. So, the exact numbers, I guess, would just depend on how fast your GPU and CPU are. But small things, maybe CPU, but for most things, GPU is going to be faster.
Just to set some expectations for something that benefits a lot from the GPU, you might expect 10 to 100 times speed up, but don't expect 1,000 times. Don't believe in
But in general, the bigger the operations, the bigger the array, the faster the GPU is going to be compared to CPU, and the faster the Numpy is going to be compared to PiTorch, to regular Python. Okay, so now we're on to just math, linear algebra. Please refer to the docs, because there are however many. Yeah, I mean, it's linear algebra. There's every function you can imagine. There's sums and means and exponentials and logs and whatever function you would expect. They're all pretty well documented. They all return exactly the same type that they got in. So, and they will all work on the CPU or the GPU. So if your x is a CPU function, it'll run the CPU version of the code. If it's on the GPU, it'll run the optimized. Next, we have some indexing. This is, I guess go up a little bit. This is very similar to what we saw in Numpy. As I said, it's inspired by Numpy. A lot of the same syntax applies. So x1 colon means take the first row and take everything in that row. So you see this is row 1, and then it pulls out just row 1. All of the a lot of the same kind of slicing syntax applies. And you can refer back to Numpy for the actual details. And if you have indexing specific questions, let us know.
So can you add a Numpy tensor with a torch tensor? Does that work? Or
You would have to first put it into. The only thing that you can add to a torch tensor are single constants or another torch tensor. So what you would have to do is you have to call torch.fromNumpy and then add it. And you might have to move it over the GPU too. So if you just want to add a Numpy tensor to something that's on the GPU, you got to move it into a tensor, and then you got to move it to CUDA, and then you can add them. And this gets a little more complicated when we deal with variables, which is the next section.
If I remember correctly, going back and forth between Numpy and PiTorch is like essentially free in computation.
Yeah, and it's the CPU to GPU that takes cost. But now we're going to start talking about variables. The problem here is that torch tensors by themselves don't support differentiation, which was kind of the whole thing that I sold you guys on, that differentiation is helpful. What they use for differentiation is variables. And variables are not the same as tensors. They look like tensors, they act like tensors, but be very clear about the difference in which one's which. Variables, they hold a tensor, and if you have a variable, .data will actually get you the tensor, which is the data storage. So tensors are basically your data storage mechanism. Variables have a tensor, but they also track the path that you went through to calculate that variable. And it's the variable object that helps you do differentiation, and the tensor is just the data that you're passing back and forth. So variables wrap around tensors. So if you want to get a Numpy array into a variable, you would have to take the Numpy array, call from Numpy to get it to be a tensor. You can call .CUDA to get it onto CUDA, and then you could put it into the variable constructor to get a variable. So you would have to go through all those steps to end up with your GPU variable, but kind of like we were talking about earlier, where you can't add a tensor on the CPU to a tensor on the GPU. You also can't add a variable to a tensor, and you can't add a tensor to a variable. So only variables can interact. That means if you have a tensor and you want to add it to a variable, you got to upgrade that tensor to a variable first. So you'll find yourself wrapping almost everything you do into a variable. Because we're doing machine learning, almost everything's going to be differentiated. So in general, most things are going to end up in a variable before you start using them. And if you try to do something with a variable and a tensor, you're going to get a similar error to the one we saw before. Yeah.
For homework, are we allowed to use this, or do we have to
for part 2, this is the one. For part 1, it's really, we're trying to make sure you guys know how to differentiate and do it in Numpy. So part 1, unfortunately, you can't do this. And you can't use SymPy or anything else that automatically differentiates. But part two, definitely use this because it's going to be hard to get good results efficiently without GPU, et cetera.
One point to make note of is y is different from a variable that just contains the necessary data. It contains like all the history and stuff. So if you create a new variable that contains 0, 1, 4, 9, 16, it's not the same as y where you created by squaring it.
Right. So we have a variable. This variable, we set requires grad equals true. That means it will, when you call backward, it will only calculate with respect to things that say requires true. So I guess stepping through each of these, we are creating a variable. We're saying y is the sum of x squared. Y is also a variable. Because when you sum variables, you get variables. You sum tensors, you get tensors. Then we call y backward. When you call backward on a variable, notice there's no like with respect to there, because I mean, who differentiates and just like there's one argument for it? But it's implied. What tells you the with respect to part is requires grad. So y dot backward means differentiate y with respect to everything that says requires grad equals true. And then if you want to see what the variable, and then y dot backward doesn't give you anything. So it's like I just differentiated where to go. Where it went is x dot grad. So in order to differentiate something, you create the stuff you want to differentiate with respect to, with that setting true. You do your calculations. You call backward on the thing you want to actually differentiate. And then you go back to the variables, and you can get the gradients back from those variables. So it's stateful, but that's the way it works. If there's any questions on differentiation, because that's a pretty important one. No, you would only just call the grad on the final item, and that grad will pass all the way back through all of your variables. Now, you will notice that this is the reason that works is it's a stateful API. What I mean by that, it's not just like you don't just call it with what you want and it gives you the results. It's modifying something that's not actually obviously in the code. So part of the statefulness is, I think, on the next section. So that .grad is shared. If you want to differentiate something two different ways, you've got to create the variable, do the backprop, and then do another backprop, and you can actually look at the grad for each of them, but it's something you have to statefully look at. This is just an example of what we talked about before, of you can't mix them up. So this is trying to, so this is matrix multiplied two tensors, it's fine. Matrix multiplied two variables, it's fine. Matrix multiply a tensor and a variable. Here's the error you get. Remember that error. You will, as I said, you will see this kind of thing frequently. If you put stuff in the wrong place, it'll say invalid combination of arguments. And you're looking for something that says variable but got a tensor. So anyways, another important thing is, as I said, it's stateful. You need to zero your gradients. So this dot backward, it doesn't just calculate the gradients. It calculates the gradients and adds them to this dot grad. So if you call backward 2 times, you're going to get double the gradient you expect there. And if you don't remember to call zeroing the gradient before you do that, then it's going to accumulate. So this is an example of differentiating again, and the grad is increasing, versus if you call grad. So grad is a tensor. Sorry. Yeah, so grad is a tensor. Oh, sorry, grad is the variable. The data is, as we said, the way to get the tensor within the variable. And then .0 is making that tensor's data reset to 0. So this is an example of manually clearing out the gradient before I run differentiation again. So there are easier ways to do this for every single variable, and they're helpers, which we'll see later. But it's very important to zero your gradient, or you're going to get weird results. OK, so I think we're getting close to this particular tutorial. As we said, the last part, we talked about AutoGrad, we've talked about GPU. Now we can talk a little bit about the neural network specific things. And the main base class is called nn.module. That's torch.nn.module. Modules are your classes which hold all of your machine learning models. So modules like store your weights, and they run your actual forward pass and they run your backward pass. So you'll create a module for your network. And modules are modular, which you could guess from the name. And that means you can make modules into other modules and include modules within your modules to try to build bigger modules. So there's a module called linear, which is, if you want to guess, it's a linear layer. There's a module called sigmoid, which does a sigmoid activation, and then another module called linear. There's a module called sequential, which can chain together a bunch of different modules. So net, in this example, is a module. It's a module of type sequential, and it contains those 3 modules. And basically what that means is when you run net, it's going to run each of these modules, and it's a way to pull your code together, keep track of all the parameters, things like that.
I've seen people create neural networks where like net is basically a function and these 3 are global variables. Don't do that, because like, if you do that, you end up basically implementing your own version of module. And it's not advised.
Yeah, you definitely want to use module. Try to use things like sequential whenever you can, because this is like a very short and simple way to, this built a network right there. This is ready to put data into and train and do whatever you want, just by calling sequential, linear, sigmoid, linear.
Yeah. More it would be of like the second.
Yeah, so if you're trying to make something that's more complicated than just a sequence of other modules, although this example is literally exactly the same as that, but it's more flexible if you want to do more other things. So what it does is never forget to call the super initializer, just in general when you're writing Python code, or when you're writing any code, really, if you derive from the base class. But if I said layers and I gave it a list, then PiTorch is not configured to look within that list, and the module would not work correctly.
Yeah, it looks at
If
like,
you, yeah.
it looks at the kind of variables for modules, and the list is not a module, so you'll
Yeah.
like ignore it.
Yeah, so in order for a module to be, in order for a submodule to be part of your module, it must be set as one of the attributes of your function. If you want to do a list, there is a module called module list. And if you're going to have a list of modules in your function, you have to use a module list, not a Python list, not a dictionary, not anything like that. You need to have that particular type of list. But what this does basically is your initializer creates everything and assigns it to an attribute, as we said. And then there's a function called forward, which is your forward pass, obviously. And your forward pass is just calling the layers on the inputs. So it takes the input, calls each of the layers, then returns the output. Pretty straightforward. And the backward function is implied. So that's kind of what makes it an autograd. That's what makes PiTorch nice, is you just write the forward. You don't have to write the backward in your homework 1. You have to write the backward yourself just to know what it looks like. OK, and then probably the last set of things here on PiTorch usage. Saving and loading is very important. By the way, if you look at this and you look at the Numpy, you'll see they're in kind of a similar order of things, just to get a sense of how to do things in one and the other. But yeah, so saving and loading, you can get the state_dict keys, which give you all of basically the weights. And the state_dict itself is just a dictionary of your variable name to the variable value. And the torch save function will save a dictionary. So you can chain the two of them together to save a dictionary. And the dictionary you're going to save is the state_dict and give it a name. And then T7 is a standard extension, doesn't matter. And then when you load a state_dict, you can give the, you use torch. So torch.load loads the dictionary. Then you're passing the dictionary to load state_dict. And the state_dict pulls out the dictionary and then saves that dictionary. So sometimes you, it is just a dictionary. So you will frequently take multiple dictionaries, put them together. Like you can do other dictionary type things here for saving and loading. You can save any dictionary of tensors. It doesn't have to be a state_dict.
It turns out you can save the network itself, but it's not advised because if you change even a small thing in your network, then like it stops working. So we recommend saving the state_dict.
Yeah. So if you make some modifications to your network, but you keep the names of all the variables the same, then you can still load and save from like slightly different versions. Yeah. So that is all of your just using PiTorch and the nuts and bolts of it. Any questions there on doing linear algebra, differentiating, etc.? OK, I think we're good. Yeah, so then now we're going to actually show you how to put this together into training a model for your homework, for example. So what this example is going to do is it's going to create a model, which is one of those modules we talked about. It's going to create a data set, which is the whole process of getting something into Numpy, moving it from Numpy into a tensor, moving it from a tensor into a variable, and then sending it into your network. And then there's just the actual loop, the main loop, which is train it, train it, train it. So we're going to go through each of those steps. The task we're doing is a pretty small task. It's basically just counting the number of ones that are in the input. And to make it a little more interesting, it's going to do the output in binary. So this is an example of what we want it to do. If the input is this, so this input has 3 ones in it, then we want it to output 0, 1, 1, which is 3 in binary. So it's just going to do a count and then output some zeros and ones to tell us the binary encoding of the number. It's an arbitrary task, but it's something simple. And here's how we do it. OK, so we start off with making a neural net module, as we said. The lines here, create a module, make sure you call the initializer. You've got one parameter, which is the size. What? No, well, so normally you would put a sigmoid layer there, right? If you want the outputs to be between 0 and 1, you would normally have a sigmoid layer. But when we show you the criterion, we're going to talk about why that's not the case. But I guess if anyone wants to guess why we don't have a sigmoid layer? Any guesses? Sorry? Well, it's also true, but it's actually for numerical stability. That in, I'm sorry? Yeah, sigmoid is 0 to 1, and we want 0 and 1 values in our outputs. But what we'll talk about a little bit here, which is kind of a tangent, is you almost never end your network with a softmax or a sigmoid, which is funny because we always talk about doing that, don't we? Yes, we do. But in practice, numerical stability means you actually combine that with your loss function afterwards. I'll do the math really quickly if we have time. But we will show you the reason why next. But it's very important to keep that in mind, that you tend not to end on those. You tend to combine them with your loss.
Yeah.
So
in this simple example, we used like a kind of very simple loss function, but in general, you'd use a loss function that basically does the sigmoid for you, or the softmax, or the whatever.
Right.
So that for numeric stability.
Yeah, in most frameworks, you will combine your sigmoid with your cross entropy to have this sigmoid cross entropy, which does both of them and is more stable than actually having a sigmoid layer. So loading data, this is just some Numpy, but basically, I guess it's worth pointing out the functions you guys haven't seen yet. But binomial is a nice little function. It's producing zeros and ones with a given probability, 50% here. So our input data is just some zeros and ones. Our labels are, we want to count the number of ones. And then this unpack bits is what you can use to convert a number into its binary representation. Practically, you're probably not going to use that much of your code, but it's nice to know. But anyway, so this is just generating out data and some binary labels. Oh, if you guys want to look at the code of this, by the way, if you go up a folder if you go to the same folder where the other two tutorials are, there's a .py file. And if you open that one up, you can look at the full source code as opposed to just individual screenshots. So then the next part is we've got our model, we've got our data, and now we've got to train it. So keep in mind that to train it, we've got to get everything into variables, not arrays, not tensors. So we got to convert them all, we got to move them to the GPU, and we created some helper functions to do this, which I think on the next slide. All right. So this function here is just getting something into a tensor, which is calling from Numpy. And then this is that if statement we were talking about, which is just a helper function called toVariable to make it easier on us. And all it's doing is checking to see if you have CUDA. If you have CUDA, put it onto CUDA, and then return the variable, whether it's CUDA or not. But it'll return the appropriate variable. Next up, we got to train the network. So we got to choose the loss function. We got to choose our optimizer. The correct choice for this type of problem, when you need to have, this is a multi-class labeling. So the way to think of this type of problem is you've got 3 outputs, each one's independent, and you're trying to maximally predict each one. The correct choice for that would be binary cross entropy. And in terms of optimizer, we used SGD, but as we see in class, there are many different optimizers. You can pick and choose, try your favorite. It's a lot of optimization. Everyone's got their favorites. But basically, we're going to create a data set. We're going to load everything. And these are the steps we need to do. Reset the gradients. Never, ever forget that. You run the data through in the forward pass to get the loss. Then you run the back pass. And then you actually do your updating. And then you always want to have some sort of progress bar or print the loss or record something because you don't want it to go into a void. So basically, you're going to be writing these steps in a loop for pretty much all of your PiTorch programs.
It can be kind of hard to see where in the code each step is happening, so like we added some comments.
Yeah, we'll definitely have to point them out.
So for instance, like we created the optimizer, we like specified the loss function, we went, and then like we went to CUDA. That's another boilerplate step. But then where's the forward? So this is the forward pass. We call our network on the input, and then we do our backward, loss.backward over here. over here we've updated the network by using a step function on the optimizer. And like, I didn't do the bookkeeping over here, but in general, that's recommended.
Yeah, this is actually, I realize this is a slightly different version than the one that's on GitHub. So look at the GitHub one, and I'll update this. But the correct loss for this one would actually be it's BCE loss with logits, I think is the right name. If anyone has the Python notebook, let me know what the name was. What is it? BCE with logits loss. Okay, yeah, BCE with logits loss is what we were talking about earlier. That combines a sigmoid and the binary cross entropy loss. So we see that actually would be the right one to use for that loss function, and that'll combine everything together. And the one on Python also has a little bit of printing out the current data, just to, but you guys know how to print. I did say I was going to just mention really quickly. Has anyone heard of logsumexp? LSE, logsum. Okay, that is the reason why we do all of this. That was the reason why I was saying not to include the sigmoid, and the reason I'm harping on this is if you forget and you use the wrong loss function, then you'll end up having like 2 softmaxes or something like that. But what it comes down to is, let's say you have something of the form log of e to the a plus e to the b. This is not stable. If a is big or b is big, you're going to end up with like ridiculously large numbers, adding them together, and then trying to take the log of them. And that looks really ugly. Yeah, and it'll overflow your computer, and it'll break, and nothing will work correctly. So the way we do this is the log of e to the a minus c plus e to the b minus c. What does that equal? See, minus c, when you're subtracting an exponent, what you end up with is e to the a over e to the c plus e to the b over e to the c, right? Just basic math, but it's good for you guys to know these. And what you end up with here is that equals to, sorry, I can't write, log of e to the a plus e to the b minus log of e to the c. Log of e to the c is c, right? So what we have here is that log of e to the a minus c plus e to the b minus c plus c equals log of e to the a plus e to the b. And that's the logsumx trip. And it seems a little weird, but this comes up in almost every single loss function because you're dealing with probabilities all the time. So like this log of e to the a plus e to the b is really unstable because a and b can be really big. What it means is you can subtract an arbitrary constant from a or from b, or I'm sorry, from a and b. You subtract the constant there, and you add it in here after the log, and nothing's changed. But if you do this, you can make a reasonable number. So what you actually tend to do is c. What you tend to do is c is the max of a and b. So this is the function that is actually being used behind the scenes. It's called logsumexp. There is a built-in operator for it, and sorry. Yeah, so the bottom line function you need to know is this thing will come up all of the time in your networks when you have something like a softmax or a sigmoid and you're trying to deal with the data. This makes it numerically stable by subtracting out the c. If you don't do that, you're going to end up with really ugly numbers. So any questions about the basic form of logsumx? No? Okay. So where that gets interesting, I'm just going to, oh, did it count over? I think we're done with this. Yeah. But yeah, so the training routine, you've got your for loop, and I think we've got like 3 slides left.
Basically just maybe a little note on the computational graph, and then we're done.
Oh, yeah. Well, this is just that during the forward pass, it makes a graph. It records everything that went into it. And then as we go through it, when you call backward, it undoes the graph. So you can see the backwards. This is a very bare bones system, things that you're going to do in your actual code. are command line arguments, saving your data, saving your model, performing evaluation on test sets. All of that type of stuff is not in our example, but you can imagine how to do it. And just really quickly, we're going to mention some libraries. So you notice that in PiTorch, there's a lot of stuff you do every time, like you create this, and then you run the loss, and then you zero everything, and then you loop through your data. There are some that you have to write yourself if you're just using PiTorch, but there are some libraries like Inferno, which are worth looking at, and they will handle the actual like looping and logging and all of that stuff for you, because we care about the machine learning side of things and your math, and we don't care about how well you can like loop and write a CSV file. So like this can handle the CSV file stuff for you and the saving, and then you can just focus on the actual data. Just really quickly, other libraries that are worth knowing. TensorFlow is the main competition. Be aware of it, but it does, it functions very differently. We decided not to do it in this class because it's got more of a learning curve, but if you have any TensorFlow questions, just let me know. But we're not supporting it in the class. My personal bias. But what TensorFlow does is you build a graph ahead of time and you run data through the graph as opposed to kind of doing things online. SciPy is good to know. It's got sparse matrices, clustering, a couple good functions you might be looking for. Scikit-learn also has some, SVM, PCA, basic machine learning, or more stats than machine learning, but still handy sometimes. Yeah, classical stuff. It's got a lot of that embedded. OpenCV is good to know if you guys are doing any image processing. It's got all of the rescaling, rotating, whatever. NLTK is good to know for any language stuff you guys are doing. Any deep learning on language, that's got your tokenizers down, the corpus, the parsing, all of that. SymPy is good to know because it will let you do symbolic differentiation. So you can actually run differentiation or integration and print out the formula, which isn't so useful for the actual machine learning, but if you want to check math or just you're in a situation where you need to differentiate something, good to know. There's also a bunch of other competition like Caffe, Theano, Keras, deep learning for Java. That's our last slide. So I think we barely made it. Okay, 5 minutes late. They're lining up. Okay.
There's no barely, we did it.
Okay, we did it.